Good day to you from Anagalactic, and happy winter. The rains finally came. We're having chilly nights, so the heat wave is over. A record-breaking heat wave. So I did my best work during that heat wave, but my research has taken off in all directions. It certainly is useful in every way, but in order to present this geometry, I've had to consolidate. This is a major discovery. But I've also canvassed the papers and books out in the field that have to do with spherical geometry, going all the way back to the beginning of time. The very first mathematical treatise was produced on spherical geometry. But the way I use the term spherical geometry is utterly unique, because I'm actually approaching the sphere in terms of its geometry, not in terms of linear geometry. Linear geometry is quite specific. The reason that we don't think of it as a specific kind of geometry is because it is the only geometry. When one says geometry, one means linear geometry. Well, I don't, because the universe does not define geometry that way. That actually is the problem in a nutshell, is that linear geometry is being used to define spherical space, which has its own geometry. That's what I discovered. Now that has several immediate ramifications that have to be addressed, which seem insurmountable, and I've surmounted them all. So there are no hurdles left to accepting, at least theoretically, I'm forced to put it that way because of the process of science. A discovery has two distinct levels. Only one man can make a discovery. But it's not a discovery, so the word discovery is used in two separate ways. The same way the word line is used in two separate ways. We have the same word to describe two completely different concepts. Well, not completely different. That's actually the problem, is that they're superimposed. The same thing is true of several other concepts that I could name. For instance, dimensionality. Very commonly, and in fact just recently I heard again for the nth time, that dimensionality, the concept of a dimension, has two completely separate meanings. But again, not completely separate. A dimension we think of as 0, 1, 2, 3, or 4. And those are the basic dimensions. There are, of course, higher dimensional spaces that have been mathematized. But actually, it starts to get stranger and stranger for fairly obvious reasons, because you're introducing hypercomplexity when you go past 4D. 4D has to be complexified. It's not strict complexification, because that is limited to the 2D concept of complexity. Now, all of these concepts that I'm just introducing right out of my hat, so to speak, are necessary as terms to discuss sphericity. So in our approach today, I'll be covering what I discovered from Wikipedia and from ResearchGate and several other sources, including a new source that Google has introduced called ChatbotAI. And it's simply when you type in a search string, at least in my browser, it offers something from the AI system to help you get a concept of what it is you typed in to the best of its guess. And when I typed in intrinsic spheric geometry, now you may wonder where I got the word intrinsic from. It was from the prior search, which I've typed in more times in the past that I can recall, just trying to find out if anybody has ever stumbled upon or conceived or theorized a spherical geometry. The answer is no. Nobody has ever even dreamt of it, which is I have got to emphasize, If that surprises you to the point of dubiety, well, you're just being a good scientist if you doubt my statement. I can no longer doubt it, but every time I say it, it surprises me again. It's like you just pinch yourself to see if you're awake. How could I be the first man to discover spherical geometry? Well, I've attempted to explain that in 760 lectures over the past 2.5 years. And what that's done, I can't say for the public, but I can say what it's done for me. It's helped me get further and further into this topic. Now, the last time that I typed in the search string, spherical geometry, of course, as you could imagine, one of the first articles that comes up is the Wikipedia article. And I tempted myself to read it again, and sure enough, I don't know if it has been added to the definition, because Wikipedia is updated continuously. So the articles can change, and sometimes subtly so that you don't notice the change. But whether I overlooked it or whether I didn't think I could pursue it, whatever caused me to not see it, for instance, it not being there, this time, just over the past 2 days, I discovered that there is a two-class system for approaching the sphere. And it's a duality that you may be familiar with. I can just tell you I am perfectly familiar with the concept of intrinsic and extrinsic approach to the sphere, because in spherical rotations, particularly for airline pilots, you had better master the difference between intrinsic and extrinsic coordinates. It's really the intrinsic or extrinsic orientation to the frame of reference. Whether you're orienting yourself according to you sitting in the cockpit, or if you're orienting yourself outside where you're sitting, essentially. And these are two diametrically opposed ways of looking at the frame. And if you get it backwards, you will lose your life. In a high-speed plane, you could easily lose your life by getting it wrong. So that has to be mastered. So all pilots know what intrinsic, extrinsic means. But in geometry, it needs to be, of course, more rigorously defined, because this is where the whole concept arises. In the approach to the sphere, it is possible to treat the sphere as a surface, and that's common to both points of view, because the sphere is, strictly speaking, only the surface. It's not the inside, and it certainly isn't the outside. But it's very important to realize it's also not the inside, which is called the ball. And that is a complicating notion, but in certain contexts you have to distinguish. Well, just approaching the sphere, we don't need to worry about the ball because it's not germane to the geometry, which only deals with the surface. Now, the way you can formulate, that is, axiomatize is the correct word, the way you can axiomatize the sphere as a geometry is in one of two different ways. One of them is extrinsic, and that's the one that's always used. It's always used. That's why we take it for granted. So what's the difference? The difference is superposition. In the very simplest way, when you have a sphere, what is the first thing that you learn in class about the sphere? That it is 3D. That it is 3D. It's 3D. What does that mean? I hope you know, because it's critical to the concept of extrinsic geometry. All geometry that we've ever used is extrinsic. There is one exception that could be stated, which is the geometry of the single line. That is just the geometry of the line. That took centuries to figure out. And it was only fully figured out by John Horton Conway And no, he did not get a Nobel Prize for that, nor was he even considered for one. And that should tell you everything you need to know, but I don't want to go there. I'll just leave that open for your homework if you want to think about the real value of the modern Nobel Prize. Now, for our purposes, we are trying to understand the sphere itself in terms of modern physics, because the sphere was discovered at all scales in the 20th century. That is a completely true statement. I know it sounds amazing, but I want to conjoin that startling fact that physics only discovered the sphere in the 20th century, but it discovered it at all scales. And there's quite a few scales to consider. So without going off on that tangent, which I've covered in previous videos, what we're dealing with is the intrinsic sphere. The intrinsic sphere, which does not have a superimposed grid. There are no lines. There's no linearity. And this just baffled the Greeks, and they gave up completely. And physics has never taken up the challenge. Nobody has ever even tried to compose the intrinsic geometry of the sphere. Instead, what you'll find in all the articles on spherical geometry, it's not geometry, except in a derivative sense. It's extrinsic linear geometry that's superimposed on the sphere, which means that physics has no concept whatsoever of spherical space. And the bald-faced fact is, the universe only uses intrinsic spherical geometry with no linearity. So that implies that it's incomputable. That's what the Greeks thought, and that's what everyone has thought ever since. That's why you got a whole plethora, again, one of my father's favorite words, a whole plethora of a brand new breed of scientists, very close to being the literal definition of breeding. That these men were bred, they were selected by an unnatural process of selecting the type of mathematicians that are needed for technology. Well, that's a one-to-one correspondence with linear extrinsic geometry, which is responsible for the Einstein energy equation, the Einstein field equation, and all the wave equations in quantum mechanics, of which there are 4 major types, all synthesized by Paul Dirac into one virtually useless wave equation, for which he is honored because nobody understands it. Because like the Einstein field equation, and in fact very similarly to the Einstein energy equation, they cannot be understood. But they work. They work without being understood. Einstein objected to that, although he was responsible directly for the formulation of quantum mechanics and the formulation of general relativity, both of which are extrinsic linear geometries. Nothing to do with curvature at all. That's why we have the calculus. That's why we have the complex number system, is because linear numbers cannot compute spheric space. It's never been done, and it can't be done. But I discovered how the universe does it. It's by composing its own derivative linear numbers, these are the computable numbers, into its own 2-component system, which we call fractions. But they're not all the fractions. It's a subset of the fractions based on unity and based on computability. Now, we're forced to select the computable numbers, but the miracle is that the 2-component number system that I discovered in 2022 parameterizes spherical space, not just the sphere. It parameterizes the universe. So it is a linchpin and the only access portal to getting the theory of everything, which I will continue to use, even though it's a misformed term. When you know the exact definition, which I've given in several videos, what is the theory of everything conceptually? Very few men will ever tell you what that is, for a very good reason. They have no idea. That's very difficult and strange to say, though, because I accept the philosophic principle, which Einstein and Emerson and several, you could say a whole class of scientists, really the majority of scientists throughout history, have assumed. That is, as a basic principle of orientation toward the universe and toward science and toward mathematics, meaning geometry, of course, that everything can be understood. And we know we can do it. We just have hit a roadblock which is frustrating people to the point of psychosis. Remember, this is in a scientific context. Nobody's running naked through the streets like Archimedes, although that's probably a myth. But he might have, who knows. So what we want to talk about today is a brand new form of geometry called intrinsic geometry. However, when you look it up, the the Google AI interpreter, which gives you your top of the list definition according to its mechanical brain, it's really selecting information from a database. And so the presentation of what intrinsic geometry should be is accurate. But then when you check to see what Wikipedia says about it, it says nothing. And there are no reference, there are no links, there are no papers. Nobody knows how to even do it. So the AI system says that it exists theoretically. What I'm here to tell you is I discovered it actually. The very first intrinsic geometry. And it's just remarkable to say, and perhaps, although I haven't thought about this, it is possible that it's necessarily the only intrinsic geometry is in fact spherical geometry. But now I'm able to say, at least according to the AI engine, which is not getting its information from nowhere, it's not thinking things up by itself, never be fooled in that direction. It can't think. What it does is select what's given to it as most appropriate to answer the question. So it is known of, and of course it is, all pilots know this, but the intrinsic-extrinsic relationship is abstract and can be applied in several ways. In our case, it's to form a computable geometry. Well, so far there's only been one, and you know it always features the word linear. So spherical, the way it's being used in science today, is strongly misleading, except it's superpositional. If you assume that linear geometry is the only way to do things, which science is always, it's the only thing that about science that has been consistently maintained, that it is linear. It's based on Euclid. Nobody has ever questioned that. And the concept of non-Euclidean geometry, you could say there's a valid aspect to the Gaussian, the Lobachevskian, and Bolyayan systems of, but that has to do with a parallel postulate, such that a right triangle on the surface of the sphere will not add up to the right number of degrees. Because in linear space, we know that that's, I believe that that's 180 degrees, am I correct? On a sphere, it's more. And in elliptical geometry, which is considered to be the converse of that which is typically called hyperbolic geometry, they're related, but neither of them is particularly useful, except, as always, in the superpositional linear context. Now, what's left out everywhere, just like a black eye, is nobody can compute curvature. It just has never been done. But I found out how to do it. So that's how we're going to be approaching the matter. I thought that this might help you orient to what is, after all, a very strange concept. And I hope I have let you know through this brief, very informal presentation that we're talking about intrinsic spherical geometry in a brand new sense that's never been researched. It's never even been surmised. Except, again, somehow, somewhere along the line, it was surmised and discarded. Otherwise, we would not have the ChatbotAI machine informing me that there are two classes of spherical geometry, intrinsic and extrinsic. And then the remarkable fact is, what is the percentage of research being done, or ever has been done? 100% in extrinsic, 0% intrinsic. So that's strongly indicative of something that is missing in modern physics, especially given the fact that we discovered sphericity at all scales. That is the definition in one sentence of the breakthrough in modern physics that separates it from everything from a century ago before to a century ago till now, is that we discovered intrinsic geometry that we still have no idea what it is. We discovered it. We just have zero understanding of it. I offer that understanding on an absolutely rigorously proved mathematical relationship between linear systematic space, and actually just linear space, and the spheric space that I discovered. In other words, I discovered that the sphere has its own intrinsic geometry. What makes it different from linear geometry is, first, linear geometry uses a one-component number system that thereby has to be, you use add using the Pythagorean theorem to get a concept of curvature. And then you need the calculus to interpret it, and you need complex numbers to interpret the geometry of it, neither of which have worked. Now that's superpositional, because actually those two tools have given us all of our technology, and that mesmerized everybody. All of this is just remarkable to say. I'm just flabbergasted at the breadth of insight offered by this simple superpositional overlay. It does not take the place of linear geometry. It simply improves it, because now you have two systems of analysis, one of which is accurate for curvature. And this becomes especially important when you consider how in the world would anybody parameterize the sphere on rational numbers, which is what I did. It has to do with the fact, which took me a while to discover. After I formulated the correct geometry and the correct mathematical system, it took a while, but it was theoretical. I wasn't sure if it was going to work. I had a working theory, but I faced one last hurdle, which I finally realized is completely solved when you realize that every sphere in the universe has a superimposed circle called its equator of rotation. All spheres rotate. So all spheres in the universe, from the tiniest, from the proton and electron, to the atom, and then you have to go to macro scale to planets, stars, and galaxies, all the way out to the edge of the universe, and you have to include the supermassive black hole concept at least to somehow explain that. That geometry is a geometry not only of space. So our extrinsic geometry, which is a grid, space-time is a grid. It's a grid. And the wave equations attempt to linearize the measurements, and that simply cannot be done for reasons which I have proved. So the grid cannot be used because it's extrinsic to reality, but spheric geometry is not. It's an exact match on reality. And it all has to do with what Einstein discovered is the relationship between space and time. That's actually incorrect. That's not true. But it's superpositional. It's true in the linear context, but you still need complexity and you still need the calculus. And I've proved that that means you fail. But it's superpositional. It hasn't failed us for technology, but we've mesmerized ourselves to think that that gets down to the ultimate structure of things. And you know that the quantum paradox has put cream pies into every face. Paul Dirac died with a cream pie on his face that he slapped into his own face because he was an honest scientist. Einstein was also an honest scientist, and he slapped the pie onto his face before he died. They died frustrated and humiliated because they knew they had failed. They failed. What they didn't fail was the government. Both of those men served the government exclusively. Neither one of them particularly intending to, although Einstein, you would have to say, did have some vested interest in his service to science. But Paul Dirac was pure, and he was more frustrated even than Einstein. He died an unhappy man because his life's work was a failure. I am here to justify the faith of Einstein and the faith of Dirac, but not the faith of Feynman or Bohr, both of whom are extraordinarily good linear scientists. And now you have to distinguish between two kinds of scientists. Every scientist except me so far, and me, because I am not a linear scientist. And I have the theory of everything and the definition of the quantum and the absolutely accurate definition of the collapse of the wave function. It's rational, and I've used the work of Ruger Josip Bošković to normalize two infinities, and I've also discovered how to rationalize the two universal infinities, and therefore I have the TOE, the two-force dynamic system, which simply cannot be seen. It cannot be seen. It cannot be perceived. It will never be discovered in any other way than the way I discovered it. You must master a very simple form of geometry called spheric geometry. It's so simple that I can teach it down to the high school level and below in one day without a problem. Everyone in the classroom will understand it. And once you have it, you have the key to everything. So that's 30 minutes. I hope you enjoyed that. Very informal, but again, within a few days, I'm going to have a consolidated approach that I'll be using this pane over here for documentation so you can follow along, and I'll have links to the paper which I cannot submit anywhere because I'm not part of an educational institute, and neither Archiv nor Vihra accept submittals from anywhere except an educational institute, and I'm not associated with one. It is possible that I can obtain an account at our local university, and if not there, perhaps elsewhere, but for that, I would have to be noticed. So far, if you've noticed me, you're the first. I hope you stay tuned. This is Anagalactic. Keep looking up. There's a waxing gibbous moon, but it's still beautiful up there. There are a couple of planets up there in the night sky. Beautiful clear nights in parts of the United States at this time of year. Here it's overcast right now, but we're very grateful for that after the devastating heat wave. All right, so we're going on with science. Whether anyone else is willing to come along or not makes no difference at all. Be right back. Stay tuned.